Okay, we've got another integral today, MIT 2025, regular season number 10. We have the integral of cosine of the fourth x minus 1 over sine of the eighth x dx. Okay, I'm definitely thinking difference of two squares here, right? If you think of that as just like y to the fourth minus 1, we could factor it as y squared plus 1 times y squared minus 1, and then we could go another level and factor it again, because that's a difference of two squares again, so we could do it like this. But before I do this, you know what I want to do though? I want to kind of set this up, because for sine, for sine squared x, we can put this in terms, we can write this like 1 minus cosine squared x. And it's making me think I want to reverse the sign on this, because I want to get cancellation and deal with something simpler, reduce the power. So if I multiply in a minus sign here, I can bring a minus sign in here and flip this. And then for 1 minus cosine to the fourth, the way I want to do that is I want to write it as 1 plus cosine squared x times 1 minus cosine squared x. So when I simplify this, I'm going to get cancellation with this over here. So let's see how it's going to look. We've got our minus sign out front. Put the numerator in that form. So 1 plus cosine squared x, 1 minus cosine squared x. And then if this thing right here, if this thing right here is sine squared x, then we can put this to the fourth power to get sine to the eighth x. So I can do this as 1 minus cosine squared x, and this is all going to be to the fourth dx. And so it's not going to help that much. We can cancel one of these, right? We can get rid of this, and we can make this a 3. But then it's not quite clear what we want to do from here, because I don't really want to, because if I distribute that out, that seems like kind of a mess. I could break it up into two integrals. No, I don't think so. I think what I want to do, oftentimes one of my favorite things to do is multiply in by secant squared x over secant squared x, just multiplying by 1. But it's not quite what we want here, because we're to the third power. Like secant squared times cosine squared is just going to be a 1, right? But with the third power, we need something a little more powerful. So what we need, so what we're going to need is, let's raise this to the sixth power, right, on both these. So that way, when I multiply in, for the 1 in the denominator, I could think about this as secant squared x all cubed. So that way we've got the same power here and here. So when we do this, let's just do the denominator first. So everything's going to be cubed. So I bring in secant squared x times 1, and that's just going to be secant squared x. Now this times minus cosine squared x is just going to be minus 1 here. We still have everything cubed. And then in the numerator, I'm going to break this up a different way. For secant to the sixth x, I can write it as secant squared x times secant squared x times secant squared x. The reason for that is I got a different purpose for each of them. For this one, I want to multiply it in. So for the first one, we multiply that inside the parentheses here. Secant squared x times 1 gives me secant squared x times cosine squared x plus 1. And then the other two, we're just going to leave it for the moment. Because the strategy we can use on these secant squared integrals is if we can get everything in terms of tangent, except for 1, then we have a substitution. Because basically, let me make a little space, because I'll show you the substitution I want. What I want to do is I want to do the substitution u equal to tan of x, because du equals secant squared x dx. So we already have our du. That's why I split this up, because I want to have the du ready, right? So we got our du right here. We don't have a tangent anywhere, but for that we can use the identity, because we have, and we'll write it two different ways. We have tan squared x plus 1 equals secant squared x. And of course we can rearrange this like tan squared of x equals just subtracting 1 on both sides. We can write it like this. So this is going to allow me to rewrite it, because on the denominator we can use this. This matches this. So this whole thing is tan squared x. And then up here for secant squared, we've got that formula. So before we substitute, we'll use this identity on everything. So this is going to become here a tan squared x plus 2 now. This plus 1, so tan x squared plus 2. This one is just going to be tan, I don't know if I said tan x squared, I meant tan squared x plus 1 in this case. This stuff will leave. And then this right here is going to be tan squared x, but we have it cubed, so I can write this as tan to the 6th x. And then we can go right to our substitution, because now we're all set up. Everything is either tangent or we've got our du over here. So how it's going to look, this is going to become u squared plus 2. This one's going to become u squared plus 1. This is our du at the end, all over u to the 6th. And then after all that, what's left, this is just going to be power rules. So let me clean up the board and we'll go ahead and simplify this and finish it off. Okay, so from what we had before on the last board, I took the numerator and just distributed it all the way out, divided in the u to the 6th to get this. And then from here, we just have power rule on this. We'll have minus sign out front, and it's going to become minus 1 over u minus 1 over u cubed. And then here, it's going to become minus 2 over 5u to the 5th. And then with the minus sign, we can just distribute that into each term, and everything's going to become a plus. And then all we need to do is just back substitute on it, but everything is in the denominator, so what I can do is get a value for 1 over u. Reciprocal of tangent 1 over u is just going to be cotangent of x. So go ahead and back substitute. What we get for the final solution on this is just going to be cotangent x plus cotangent cubed x plus 2/5 cotangent to the 5th x. Add a plus c, and that's it. Now, one note on the solution, this looks nothing like MIT's solution. Even though they're equivalent, they got it in terms of cosecant. I actually kind of like it this way. I mean, it makes sense to me, but maybe we should get it into their form just to see if it works. So let's clean up the board and I'll just factor this and get it into their form. Now, for the first step to simplify, what I did was I factored out 1/5 cotangent of x from my solution on the previous board, which leaves us with this. And then we can use this identity for cotangent to get it in terms of cosecant squared x minus 1. Now we have cotangent to the 4th over here. For that, we can just square this. So let's see, for cotangent to the 4th x, that's going to be cosecant to the 4th minus 2 cosecant squared x plus 1. So what I'll do is I'll just plug in this value and this value into this here. And then from here, we just need to kind of put together like terms. So let me see if I can do this on the fly, because I'm getting kind of impatient with the simplification. Because I'm getting kind of tired of this simplification. So let's see if we can put it together. So here, 2 times cosecant to the 4th. So we'll have 2 cosecant to the 4th x. For the squared terms, we're going to have 5 cosecant squared terms. 2 times minus 2 minus 4. So we're just going to have 1 of the cosecant squared terms. And then constant values, we're going to have 5 minus 5 is 0, plus 2 times 1. So we have a plus 2, add a plus c, and that's it. Okay, there you go. That's it for today. Thanks everyone for watching. Have a good day.